Chúng ta bắt đầu lại nhé. Tia đã collect homework chưa? Thì ta không có nhiều thì tất cả những gì mà mình JPEG là dạng hình mà mình xem thấy trên mạng đó. Okay. Thì nó có tất cả những gì mà mình nói về trong 2 ngày vừa qua. Okay. Thì nó it got established in obviously the year 2000. That's why we have the name. It's not popular now because mainly implementation costs. Okay, all the browser people, the people who design Internet Explorer, Mozilla, Opera, so on and so forth, they don't want to spend their time implementing the decoder for JPEG because it takes energy away. Okay, so but it's based on the Wave transform, which is the second topic of this summer seminar, right? From Angelo. So you obviously should recognize the structure before. This is an entire image, okay? Passing through, in this case, 3-level wave transform. And the unlike the DCT-based JPEG, okay, JPEG 2000 doesn't do compression locally. It actually does compression globally for an image, or at least a big part of an image. They call it a tie. Okay? So for example, if you have a huge image, they might break it into ties, 256 square. So basically large block. Okay? And then for each of the block, it does the wave transform and it does coding. Okay? The way that we do wave coding is quite different from the way we do the regular JPEG BCT-based coding. Okay, and one of the main techniques is based on the concept calling zero tree. Okay, zero tree means there is a strong correlation between coefficients at this level, and this level. So this guy, this coefficient is called. So these are the parent. Okay, and these are the children. These are the grandchildren. For example, you can think of it that way. Right, so one parent has 4 children. These 4 children have children of their own. Okay, so they got together. This branch gives you 16 grandchildren. Okay, and typically the observation is this: if a parent is insignificant, meaning small, or below a certain threshold, okay, then it's very likely that all the children is so. And the grandchildren as well will be below the threshold. Okay. Now, why is that so significant? For example, if you declare that something insignificant, you say right here that this is insignificant, then the rest will just be thrown away, and you really terminate the entire branch. You kill off the entire trees. Okay. So if you say that this guy in the encoding process, if you decide that this guy is insignificant, the rest will be thrown away, okay, because of this properties. So basically, that's how, instead of having those zigzag scan and then end a block, we will do this type of coding. And as you can see, it's very, it's somewhat related to the embedded quantizer that we studied yesterday, right? We send information 1 bit plane at a time. So the bit plane give you the threshold right here. The threshold T give you where you are on the bit plane. Okay? And if the parent is under the bit plane, then most likely all the children and the grandchildren will be under the threshold as well. So then you can just eliminate the entire branch. Okay? Now, I'm not gonna go much too deep into that, although I have the remaining, let's see how many slides. Fortunately, the mathematical part is basically over. Because in motion estimation, motion compensation, unless you do optical flow, which is very fine, at a very fine scale, there's just not much mathematics, okay? We cannot afford to do motion estimation at the pixel level. Why? Because it will cost us as much Okay, if you want to describe the motion of every single pixel, it will cost us as much as sending that pixel over, right? Why do we need to do motion estimations, right? So we do motion estimation because we would like to group a region, okay, and describe the motion of that region together, or that block, or that object, or that whatever, together, okay, using one single motion vector. That's the entire key, right? Otherwise, it's not as effective anymore. So we're going to spend the first half of the lectures on video coding approach and algorithms. So mainly, we talk about the simple video codecs and the block motion estimations and motion compensations. Okay. After we get the basic down, we will start taking a look at video coding international standard. Okay, which is you should recognize some of these names before. Okay, these are actually the type of standard codec that we use every day in our everyday life. For example, all the DVD movies that we watch and digital television broadcasts that we see every day is in the MPEG-2 format, right here. Your VCD, the karaoke CD that we come to love, comes from MPEG-1. Okay, so that gives you an idea. Now, and if we have some time, maybe we'll talk about the latest development. Okay, and the goal is tomorrow we start talking about the communications part, which is the really active area that research is still being done every day. Okay, so first let's try to understand video. Okay, and so we have MATLAB assignments. I ask you to take out frames, look at the frames, so on and so forth. So you get an idea of what it is. It's a concatenation of many different images, right? It's one after the other. And a lot of times they adjacent frames that right next to each other, the neighboring frames, right, have a lot of things to do with each other, have a lot of things in common, right? They probably share the same background, right? Whatever in the back, and maybe the foreground is moving a little bit. Okay, so we can think of a natural video signal as a sequence of still images or frames. Okay, so that's number one. Second, let's investigate the type of correlation that you would see in a standard video sequence. Okay, what type of correlation? So the type of correlation sharing the background is called temporal correlation. Okay, the correlation in time. Okay, so that's why it's called temporal correlation. So similar background with a few moving objects in the foreground. Okay, that's the heaviest type of correlation in video. And then spatial correlation. What does that mean? Similar pixels seems to be grouped together, just like spatial correlation in images. So this is what we have been dealing with so far. Okay, that's why we do transform. Okay, so that we can take away this type of correlations. When you do DCT transform, you take away this type of correlation. Okay, so that's another part of it. Since video is just consists of all the frames, if you don't take time into account, this is what you will see. Okay, and then there is usually much more temporal correlation than spatial. That's why in video coding, transform is not a critical part. Okay, taking the KLT, the DCT helps, but it doesn't really buy you a lot of compression. What buys you the most is how to take away this temporal correlation, take away the background, and only encode the foreground. Okay, that's the key. So motion model in video sequence. Let's think about the type of motion that you would observe in a natural video. Okay, so imagine you take your digital camcorder, you go outside the campus. Okay, you start taking making your own little home movie. Okay, so what type of correlation would you see? What type of correlation would you see? Will you see what is translational motion? Any idea? Translational means what? Left to right, right to left, up, down, right? Okay, object moving from left to right, from right to left, from up to down, from down to up. Translation, right? Here to here is the translation. Agree? Okay, what else are you going to see? Are you going to see scaling? You zoom, right? We like zooming. We like zoom in, zoom out, right? Our digital camcorder has that very nice button that you tend to be abusing a lot. Okay? Zooming in, out, right? So different scale. It's like resolution in wavelengths, okay? So that is the scaling type of correlation, okay? Of motion. What about rotational? What does that mean? Right. That can be two types, right? You can rotate your camera, your camera, or the object can do a circular type of movement, right? Little bird will fly like that, for example. It's some type of rotational motion, right? So you would see mainly these three types of motions. The natural motion means the motion coming from people, objects that's not related to camera movement. Okay? Suppose that you fix your camera like that camera right there. That's fixed. Okay? When you do that, well, oh, he's still moving the camera. when you have a camera on a tripod like that, most of the time you see natural motion. Okay, the motion of the scene, the motions of whatever happening around you. And then there's another type of motion, the camera motion. Okay, we like to do this a lot, panning. Okay, panning means you would like to capture some kind of you move the camera from left to right, from right to left, trying to capture a sequence of your camera has limited resolution, right? So obviously, in order to get in more information, you would like to position your camera in many different directions, trying to capture a lot more information in. And if you do that quickly, it's called panning. You can do camera zooming, right? You can do camera zooming. And a lot of times we would like to do fade, right? We fade video in, out, right? These are the type of special effects. Okay, so that can happen in a digital video as well. Now, if you think about say motion pictures, movies, okay, if you think about encoding a movie, you would encounter all this. There will be fading, okay, scene change. Typically, movies, movie directors do not like to just cut a scene like that. You never see anybody cutting a scene in, very abruptly. Typically, there's a transition period. Okay, there's a fading period to fade from one scene into another. There will be a lot of zooming. There will be a lot of panning, and obviously there will be a lot of translational, rotational, scaling type of movements from natural objects. Okay, so let's think about some very simple video codecs. Suppose that you have the state-of-the-art image codec. Okay, what is the easiest way? What is the easiest way to generate a video codec out of a really powerful image codec? Well, you can just do one frame at a time, right? So you totally ignore temporal correlation, right? Okay? Actually, there is some application in practice for that type of video codec. You know why? It's very simple. You don't need to. Okay, it's as simple as you can make a video codec. Okay, the video coder, that is the simplest video coder that I can think of. Right? Take a good, nice image coder like JPEG and just do one frame at a time. Now another advantage is that you have total random access to any frame you like. If you want to pull out frame 55, sure, there's no problem. Okay? You just search for the start of frame 55 and start decoding, right? And then you decode until you hit the beginning of frame 56, and that's it, right? So in NPAC, if later on we're going to see that seems to be a problem. We cannot randomly access any frame we want. it all takes some time. Okay, and then actually we have to think of a way so that we can have random access to all the frames. Okay, so that's one thing. Now, one of the other things that we can do is to encode the frame difference. That is the easiest way for us to take care of temporal correlations, but so to improve performance a little bit. This is not very fancy, but it will do a much more reasonable job than this guy right here, right? Because when you take the frame difference, you will see that the residue, okay, or the difference will be very, very small. And if you display it, you will see that it's mainly black. Okay? So this is something that we can easily do in MATLAB, right? I asked you to pull out a frame. Okay? So you can pull out frame 2, and then you can pull out frame 3. You take the difference, and you display the absolute value. Okay? You will see that most of the time you get something very, very black. Okay? Meaning that the frame difference is very small. If the frame difference is small, we can typically do a much easier job of compression than the frame itself. Okay, so these are simple way to do to take care of temporal correlations. But if you really want state-of-the-art video coding, you must have a very delicate motion compensated framework. It has to be much more powerful than just taking the frame difference. Okay? After all, you're trying to match a background with the foreground, right? And if you take the main difference, okay, you might be able to take care of the background, but the foreground will be completely messed up, right? If there's any movement in the foreground. And then second, there's this stability problem. Okay, background does match, but it doesn't match perfectly. What if you are just off by 1 or 2 pixels? Okay, we would not be able to perceive any difference, but the difference is there. The difference is actually there. Okay, because your hands, when you take your digital camcorder and do recording, your hand, I bet you that you can never keep it steady enough. Okay, there will be some differences. Okay, unless you can hard mount it on a tripod or something. Now, and there's also camera noise. Okay, camera has noise. It's not perfect. Okay, so although it looks the same, there's actually a lot of differences. So that's why we have to compensate for all that. Okay, so typically these are the main features that you would see in a very typical video coder. Okay, there will be the main things is we will do transform-based coding on the motion compensated prediction error. So we will do some motion estimation, okay, do predictions. The result of the prediction hopefully will be very small, okay, will be fed into a transform-based codec, just like JPEG. Okay, so we don't do JPEG on the frame directly, we do it on the residue, the prediction error. Okay? Next, the popular transformation being used would be the block DCT, okay, very popular, and recently people also would try out with it in video coding as well. Okay, now it's doing pretty well, but not as well as this guy. This guy is still the leading contender. Okay, we will do closed loop DPCM. Closed loop means what? We do prediction on the reconstruction with the head. Okay? That will make sure that our encoder decoder are not out of sync. There will be no accumulation errors. Okay? So that is always the case. And then we usually employ block translation motion model. So basically searching for translational motion only. Okay? We're going to come back to that and I'll try to explain why. Okay? Why is that the case? We talk about rotation, panning, all kind of different motions. How come we only worry about translation? Okay, the key is in the fact that you have 24 frames per second, so it's very fine. There's a really fine sampling rate in time, and typically object cannot move that fast. So it's hard to rotate 90 degrees in 1/24 of a second or 1/30 of a second, you typically do this, right? So that would take some time. And so with that fine sampling rate, most of the time, motion turns out to be translation. Okay? So all international video coding standards are actually based on this coding framework right here. Okay? They all look like this with small details. Okay? The difference between them is actually very small. The improvement, but not a significant jump of any kind. So we have video teleconferencing guys like H.6.1 to 6.3 to 6.3 plus to 6.3 plus plus, and then finally H.6.4, which is the latest guy right now. And then so this with teleconferencing in mind, real-time communication in mind. Okay, if you just want archive and playback, meaning storage and then playback at a later time, we have the MPEG series, like MPEG 1 in VCDs, MPEG 2 in DVDs, MPEG 4 in DivX. Okay? So, a typical motion compensated codec will look like this. This is the input as a frame. So frame 1 coming in, frame 2 coming in, frame 3 coming in, so on and so forth. Now, you will do motion estimation based on a frame delay. Frame delay means the previous frame. Okay? Okay, so you delay the entire frame, and you take that delay frame, you do motion estimation with the incoming frame. Okay? This delay frame comes from inverse quantizer, inverse transform, inverse entropy coding. Means what? We do it on the head. We do it on the head. This frame delay has the head, the reconstruction, not the previous frame that you see over here. Okay, so we do it on the head. This is why this is called a closed loop codec. Okay, we do motion estimation. The result of the motion estimation will be fed into the motion compensation part. This motion compensation try to reconstruct, okay, the frames, and you take the difference. Okay, so this is the reconstruction with motion taken away already. Okay, and then you do a straightforward frame difference, and then the residue coming out right here will be fed to the straightforward transform quantization entropy coding, which is very similar to a typical image codec. Okay, so this is it. All right. Now this is the encoder, and if you want the encoder, as I said yesterday, the encoder has everything. When we do DPCM, closed loop DPCM, the encoder has everything. So at the encoder, you can display the reconstruction if you really want to. Okay, you can monitor the quality if you really want to. Okay, you can just tap it right here and then show it on your monitor. Okay. Another thing that we have to encode, not only the residue, but we also have to encode this. When we do motion estimations, there will be motion vectors. Okay. Basically all the information, the psi information about the motion. That has to be encoded as well. So this arrow plus this arrow will comprise your total bit stream, your video bit stream. Okay, this doesn't go into the bit stream, right? This is for display only. If we want this to go to the bit stream, it will double your bandwidth immediately. Now, so the decoder is here. If you want to decode, take this part, okay, put it over there on the other end, and you're done. So typically, if you have the video encoder designed and implemented, the video decoder is trivial. Okay? Now, let's talk about motion estimation. So formally, the goal of motion estimation is to extract the correlation between adjacent video frames. Okay? So these are my video frames, this is my time axis, and the general problem statement can be posed like this. Given the current frame C, say the one in the middle right here, current frame C, and the reference frame R, say the previous one right here. Okay? Find the function fxy and gxy, where xy are the index of the pixels. Okay? these xy are pixel index. Okay? So find fxy, or transformation of pixel index, such that the distortion between the current frame and the reference frame being compensated like this is minimum. Okay? Now, there are many different ways. There are so many different functions that you can pick for f and g. Okay? But the translation model means fxy is equal to x minus dx, and gxy is equal to y minus dy. dx, okay, so basically this is telling you that the object is moving away in the x dimension by this much, and it's moving away in the y dimension by this much. Okay? So moving, okay, if you just move sideways like this, then maybe this guy is 0 and this guy is 2. Okay? So it can move sideways, up, down in a translation fashion. Okay? So this is a very special case, the simplest case that we can think of for fxy and gxy. Now, if we just take the frame difference, okay? What is f and g? fxy equal to, if I just want to take the frame difference, I don't do any motion estimation. What is fxy? fxy is equal to, is that 0? Right? You don't move anything. Agree? So let's think about it a little bit. If I don't do any motion estimation, I just do frame difference, okay? Then fxy is just x, and gxy is just y. I'm not modifying the index. Every index stays exactly where it is, okay? Now, if I'm moving the index, that means I'm moving my object around, okay? So that's very important. And if I assume that this translational motion, and I do this operation on a block by block basis, okay, small block at a time, then what I have is a block-based motion estimation, motion compensation framework. So it's called BME for block motion estimations, and BMC for block motion compensation. Okay. Now, if it's not that clear, okay, let me move. Okay. Come back to that block motion estimation, motion compensation in a few minutes. So hopefully it will be clear. Let me say a few more terms that I will use throughout. Whenever I say inter means I'm going to look across. Okay? So intercoding means I will do coding with some kind of reference to the reference frame. Okay? So it means that I would try to do motion prediction. Okay? So that's called intercoding. Intercoding happens when you look across the current frames. You look somewhere else. Okay? Intracoding means you do it within the frame. You don't look across. Okay? Now, a lot of times we need to do intracoding. So let's think about it a little bit. For any block that I fail to find a reasonable approximation or a reasonable motion estimation, I'll just encode it as is. Right? When do I encounter such case? When do I encounter the case where I fail to find motion? There are two very simple examples that I can give you, right? One, an airplane or a car suddenly enters the frame, right? Will you be able to find motion? It doesn't exist in the previous frame, right? We cannot find any motion for that, right? Suddenly something strange comes into a scene. We cannot find motion for it, right? So in that case, let's just encode that block just like an image, a small little image, right? So that's called intracoding. Or if you have a sudden scene change, like in the Glasgow sequence, frame 23 and frame 24 has a very sudden scene change. There's no fading. Okay, you come from the burst to the motion of the dome. Okay, there's no correlation whatsoever between these two frames. Then what do? In that case, we should do intercoding, because if we try to find any motion, we will never be successful. Okay, so a lot of times we actually need to do intercoding. Another reason why we do intercoding is for synchronization if we have a very lossy communication channel. Okay, the type of motion prediction, motion compensation that we're doing is very susceptible to channel errors. If there's channel errors, everything breaks down, right? Because you predict from a different guide than the encoder, for example. So a lot of times, if the channel is very lossy, has a lot of channel errors, you actually want to increase the percentage of intercoding blocks. Okay, that's another reason. Now, another term that we will use a lot of time is called conditional replenishment or copy. This is a very powerful mode. Okay, it's powerful because when prediction error is low, that means you find a very close match of the block. Okay, what you want to tell the decoder is just to copy the block over. You don't need to do any coding. Right? You have all the previous frame. You have the previous frame, right? You come into the current frame, and it just happens that you find one block that matches really, really well in the previous frame. What you should have done is just copy that block over, no coding. Very intuitive, right? So this is called replenishment, because we simply record the motion vectors and we call that block over. Don't need any coding. Okay? And that saves a lot of bit rate. In the demonstration later on, when we have time, you're going to see that you will see that a lot of times you actually can just copy the blocks over, and that's why we can decode DVD now using software only. We don't need any. Before we need hardware assistance, right? Now we can just do software decoding, 30 frames per second, outrageous resolution, right? And that's because more than 50% of the time, we typically will be able to just copy things over. So there are a few type of motion models, and these three are typically used a lot in computer vision. Okay, so translation is what we will be focusing on. Okay, all we will talk about in this course is just this translation model, because that's all we need to be able to design a very good video codec. There are some fancier motion models. For example, this guy will be able to take care of zooming in, zooming out, and also rotation, because you allow the modification of x and y. Okay, you pass this x, y into a matrix, so you can rotate that matrix. Okay, so for example, so this affine motion model is a lot more powerful. However, it comes at a cost. Okay. First of all, computational complexity. We need to do a lot more work, and I'm going to be able to convince you in a few minutes that doing this guy alone is not trivial. It's actually very, very costly to do. Motion estimation remains the most difficult bottleneck that we have to deal with in video coding. Okay, and second, if you have a complicated model, then you need to be able to describe your model to the decoder. Okay, so you will have, if you use this model instead of that, if you use this model, you send two things over, dx, dy, right? You need to send two things over. If you use this model, how many do you have to send over? 6. This guy, this guy, this guy, this guy, this guy, this guy. And in a lot of time, you will be trading off between the bit rate for your side information and the bit rate for your residue. Okay, so that's part of the problem. Now, so let's go back to block motion estimation. Okay, which is the concentration. This is what we would do. We have the current frame, which we're trying to find motion. Okay? And we have the reference frame. Reference frame typically is the previously reconstructed frame. Typically. Okay? But in some cases, it doesn't have to be. So that's why I'm being careful. That's why I say reference, not previous. So this guy comes from somewhere. Typically, it's a reconstruction. It has the hat. This guy has the hat on it. Okay? What you would do for the current frame is that you break it up into uniform square, like this. Okay? For each of the red square, you will do this. You will define a search window around, a general area around the red square. You will be looking all over the place in this search window, within this search window, and find out the best match. Okay? Trivial enough? Okay? So I'm going to bounce around this red box, okay, to find the best match. And in this trivial example that I draw, I'm going to be able to identify the yellow as the best match. Okay? And then what I would do is send this motion vectors over to the decoder, and also send the difference between the yellow guys and the red guys over to the decoder. At the decoder, you have this reference frame, right? You have this reference frame. You decode the residue, you decode the motion vectors, you add the residue back to the motion based on the motion vectors, okay, to the correct location, and then you put it here. Is that trivial enough? Okay? So at the encoder, we take the difference away. At the decoder, we add the difference back in. So we have perfect, okay, everything. Now, how is it? Yes?
Is window fixed? Is that window fixed?
Fixed? Or you mean the size?
Yes.
Oh, no, that's typically up to us. That's never being specified in any standard. You do whatever you want. Okay?
What about if motion vector is very large?
Is what? Is large?
Very large.
Oh, okay. It's very rare to have a large motion vectors.
Yeah.
Why? You have 24 or 30 frames per second. The object cannot just move from here to here very quickly. Okay? And if it does, forget about it. We do intercoding for this one. Okay? Okay? If it does, it's very rare. It can happen, but it's very rare. Okay? You don't want to waste time searching in a very large window. Typically, a reasonable size window. We'll talk about the size of the windows a little bit later on. But, and I have a slide showing you the trade-off between the size of the windows, is the size of the search window, and the bit rate, or the quality. Okay? And you will see that you trade off very, very little. Okay? Now, how do we know that one guy is the best match of the other? We need to come up with a criterion, right? And the criterion, there are typically two types of criteria that we use here. But the most popular is called sum of absolute difference, or SAD, or MAD, or whatever name that we called it before. This is the L1 norm of the red square and the yellow square. Okay? So what happens is you take the current block right here, you take the difference between the block in the reference frame, take the absolute value, sum them all up. Okay. Now, this is, and you have to search, okay, the index here from 0 to Rx and 0 and 0 to Ry is the size of the block. Okay? So here. This is the size of the block, Rx, Ry. Okay? And then you have to slice this box all around. And the guys that give you the lowest SAD win. The guys give you the lowest SAD win. That's it. Okay? Is that clear enough? Okay? If you find the lowest SAD, Okay, so first of all, you have to check here, right? You check here, 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 here. You check all over the place. Okay? You find the values that give you the lowest SAD, and then you declare this the dx, dy that you find as the motion vectors. Okay? You declare that the motion vectors. Okay. Now you can modify this a little bit, and instead of using L1 norm, you use L2 norm with a square here. Okay. It turns out that it doesn't make that big of a difference. Okay, but in some architecture, you are paying for this, right? Because you have to do multiplications, and in some, I think in Intel architecture, it doesn't make any difference at all. But typically, this is less complex than that, for sure. Now, people have tried other norms, other correlation measure, but roughly nothing really outperformed this simple SAD. Nothing really outperformed that by a significant margin. Okay, so we start with this. Approximately the same coding performance, and this is typically the less complex out of everything that people try. Okay, it's a very simple procedure. Sum up the differences. So the common setting is this. We typically do a macro block has the size of 16 by 16. That's what we will be using all the time. The macro block has a size 16 by 16. Okay, and the search window size is typically 15 here, 15 there. So you will be able to search in a let's see, what, 46 by 46 window. Okay, that's a very typical setting that you would see in MPEG 1, MPEG 2, for example. Okay? Motion estimation only perform on the luminance space. We never do motion estimation for CR and CB. Okay? Because they are correlated anyway. So if you find a good motion vector for Y, that motion vector is also very good for CR and CB. So let's not waste time. Okay? The chrominance is typically has smaller size, so it will be 8 by 8, and we only do motion estimation on this Y block. So let's think about strategy to do this. Okay, strategy to do this. The first is called exhaustive search. That should give you the minimum all the time. Agree? Okay, now let me explain the red dots. I am showing you the possible places for your motion vectors. I'm showing you all the possible placement of your motion vectors. So this is my dx, this is my dy, this is 0, 0. So this, at this location, it means that the two blocks do not move. This location means that the block doesn't move. Okay, the red block and the yellow block stay exactly the same at the same place. This location means the yellow block is 1 pixel over, or the object is moving 1 pixel over. This guy means that the object is moving 1 pixel up. This block means the motion, the block is moving 1 up and 1 sideways. Okay, so on and so forth. So this means that the object is moving very far away, and this means that the object is moving is very close by. Okay, and what you do is you go through every single red dot. For each of the red dots, you have to do that double summation with the absolute values. Okay, come up with one single SAD. Right? So you have one SAD for this guy, you have another SAD for this guy, you have another SAD for this guy, and then whoever has the lowest SAD out of these total wins. Okay? It's trivial, it's very brute force, but actually that's what's being done in practice a lot of the time. Okay? Exhaustive search. Okay? Now, so what is the complexity of this thing? Okay. How many operations do I need to check one dot? How many operations do I need to check one dot? Suppose that I'm going with this guy. Not 64, but No, 64 is way too small, right? Okay. This is going from 0 to 15. This is going from 0 to 15. Okay? Yes. 16 square. 16 square operations. Okay? 16 square operations just to be able to find this one single SAD for one block, right? And so to find the motion vectors, for just one micro block, how many do you need? Well, you count how many dots you need, and then you multiply by 256. Agree? Okay? How many dots depends on the search area. Okay? So how many dots do we have in this search area? How many will you be able to have? 30 here and 30 there. Agree? Right? 30 here and 30 there, right? Because you're going to take this red box and put it here, right? And then you move down. How many times are you able to move down? 30. 30. And you'll be able to move over by another 30, right? So 30 squared. That's 900. Almost 1,000, right? And then multiply by the 256 that we need. Okay? For each of the locations that we search, okay? And that is the complexity of one single square. Okay? That is the complexity of one single guy. Just one guy. Okay? Then you have to move on to this one. You have to repeat the same thing again. The entire thing. Okay? And then move to this one. You repeat the entire things again. Okay? And you do it for all the blocks here. So already you should see that this is a tremendously computationally extensive type of algorithm. Okay, it's very costly. Okay, and you have to do what? 30 frames per second. You have to be able to process 30 of these frames per second. Okay, so that's crazy. Okay, but that's what we actually need to do. So hopefully that already, now several comments, okay? It's very computationally expensive, but it's optimal in the case that it gives you the lowest SAD, okay? And it's actually highly regular. And it's very easy to parallel compute, right? You can assign one processor doing all these this quadrant, another processor doing this quadrant, another processor doing this quadrant. There's no problem. Okay, it's highly parallel in nature. So in hardware, sometimes people do parallel computations just to reduce the complexity or keeping up with the communication rate. Okay, now, but another thing that we can do is to investigate suboptimal motion estimation. Right? One thing that we can always do is to reduce the search area. Right? We make the search area very small. So that means I don't have too many dots. Okay? Maybe I only have to check 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5 across, 1, 2, 3, 4, 5 down. So instead of checking all these red dots. Okay? So you can always control that. But you have to sacrifice the efficiency of motion estimation, right? Now, another thing is trying different search strategies. You don't have to search all the dots, right? We don't have to search all the dots. Maybe we can get lucky once in a while by just doing a very sparse sampling of the red dot space, right? So there are various type of ad hoc strategies that people use for fast motion estimation. And typically they boils down using two main concepts. Typically it's either some kind of a divide and conquer approach. You kind of break the search area down to different areas and you only do very sparse sampling. Okay? You check a few number of points. Okay? Or you do some type of gradient search, where you try to move in the direction that seems to give you the lowest, the best improvement in terms of SAD. Okay, so some combination of these two will give you pretty much all the class type of search algorithms. Another thing is the multi-resolution type of search algorithms, where instead of searching on the large frame, you search on the lower resolution one. Say, just like the wavelet or the pyramid type of scheme, where you do downsampling to get the lower rate, and then you do full search here. After you do full search here, you try to interpolate the motion vectors and you go back up there. So that's another type again, it's the sampling type of search, where you don't want to check every single thing. You only want to check a small number of candidates. So I'm going to give you just a few very typical fast block motion estimation algorithms. Okay, so this is the search that that people call 2D logarithmic search. Okay, so all the green dots are the one that we're supposed to check. Okay, whatever that we check, I'm gonna mark it by different colors. Say red. Okay, so in the 2D log searches, what we do? We check. Does that show up? Can you see the yellow? This is yellow, this is yellow, this is yellow, this is yellow, this is yellow. So it's like a cross, okay? I'm going to check this guy, this guy, this guy, this guy, this guy. So five candidates. I check 5 candidates. I find out the one that gives me the lowest SAD so far. Okay? The one that gives me the lowest SAD so far, and I redo this operation on that locality. Okay? So for example, this guy gives me the lowest SAD of the 5, okay? Then I check this one, this one, this one, this one. Okay? And then out of these 1, 2, 3, 4, 5 candidates, I find the lowest SAD so far, and then I try to repeat that same deal again. For example, here. Okay? So as you can see, we only check a subset of all the dots that we're supposed to check. And whatever gives you the lowest SAD so far, you declare that the motion vectors. Okay? Now you pay for the optimality, right? Because there's no warranty. There's no warranty. There's no mathematical formula that we can derive showing that this search will always identify the best match. Okay? It's only an ad hoc solution. Okay? Maybe you can come up with your own. Okay? But let me suggest another one. Binary search, divide and conquer. Divide the search area into 4 regions. Check the midpoints of each region. Check the midpoint of each region. Find out the lowest SAD so far. Divide the region again. Check the midpoints, so on and so forth. Okay? So you can always do something like that. Again, there's no warranty. Okay? But it's fast. Okay, sometimes in order to keep up with the frame rate, you have to do suboptimal coding. Okay? It's part of the engineering trade-off that we do all the time. However, suppose that you really want optimality. Okay? You really want to keep the optimality constraint, but you want to do it fast. You want to do it fast. How do we do it? The concept is called early termination. Remember, we have the double summation with the absolute value. We have the double summation with the absolute value. That cannot decrease. It's monotonically increasing. Okay? Or monotonically non-decreasing. Okay? It cannot decrease. Okay? So early termination means that during the search of something, if it's already above the best that you obtained so far, you don't need to do further investigations, right? Okay? So for example, one thing that we can do is we can do some type of spiral search like this, okay? I start at 0, which is a very nice thing to do, right? 0 means I just take the frame difference, right? That is always a very good starting point, okay? And I find the SAD. So I have a threshold, okay? And then I keep on spirally searching outward. Spirally searching outward, like this. Okay? Spirally searching outward. Whenever I cross that SAD that I found, I terminate. If I find a smaller one, if I happen to find a smaller one, I update my best so far. So I lower the bar. Okay, make it more difficult, right? I lower the bar. And when I lower the bar enough, suddenly you will discover that for the search that at the outreach of these things, it's going to be very fast. Because within a few operations, you're already above that bar. So you get terminated. Okay? So in a sense, you're still checking everyone. You're still checking everyone. But you're not going to spend a lot of time doing that double summation accumulations. Okay? You just, if it's over, then we throw it away and we start a new search. Okay? And we need to keep track of the best match so far. That's all we need to do. This search area is being implemented in MPEG 4 and H.263 plus. Okay, so people actually do full search when they do motion estimation. Okay? Next, still optimal, but based on something we call partial matching. And that comes from a very nice observation. The triangle inequality. We all know this, right? The MAD or the SAD is basically, so instead of doing the double summation, I do the single one, but it's over all the blocks, okay? This is the absolute value of C minus R, right? Okay? And this is equal to or larger than or equal to the you know, if I put the absolute value outside, right? Okay? So that is equal to this thing. Okay? What is this? Double summation of C, double summation of R. So that's like the average of the block. Average of the current block, and this is the average of the reference block, right? Now, I can do it in one dimension, meaning that I do the average of all the rows or average of all the columns, okay? And then I do the search within the what is that? The projection, the row projection and the column projection. And based on the triangle inequality, I know that if you're not matching well in this space, then forget it. You can never be a good candidate. Okay? If you're not a good match in the projection space, okay, you get eliminated. Okay? And then you only have a few guys that you really have to check. The guys that actually pass all the row projection and column projection tests. Okay? So that is another algorithms that seems to be working really well when exhaustive full search is concerned. We want to really check everything and do not want to miss it. Okay? So this can be combined with spiral search and early termination like the one that we had before. Okay? This strategy can be combined with the spiral search and the early termination you had before. Whenever we cross that bar that we found, you get eliminated from the search. Okay? Now, so let's spend, okay, yeah, that's right. Another type of smart motion estimation is called spatial correlations. And this is based on the observation that typically neighboring blocks move together or stay together. They either move, right? You have a block, an object, which consists of many small blocks. Object moves mean all the blocks kind of moves together, or all the blocks belong to the background and they stay together. Okay? So if you already do motion estimation for 1, 2, 3, 4, correct? When you get to this guy, you already process 1, 2, 3, 4, correct? Okay? So then you have the information on the motion vector of 1, motion vector of 2, motion vector of 3, motion vector of 4. You base on that, you predict the motion vectors for C. Right? It's a smart strategy. And then you should check that prediction first. Get a very low bar. Then after that, you apply early termination. Right? So that is a very, also another smart motion estimation strategy that will lead to optimal motion judge. Yet faster, right? So let me give you a few examples. this is the previous frame of the Glasgow sequence that we play around with. Okay, I don't know what frame, maybe this is frame 24 and this is frame 25. Okay, this is the current frame that I have so far. And these turns out to be my motion vectors. You see all the red little things? Okay, the red little guys right here, they are the motion vectors. Okay, and if you come close, I'm telling you right now, they're pointing this way. They're all pointing this way. I think this is part of your math lab exercise today. Is that true? All the motion vectors, as you can see, is pointing the same way. Okay, which indicates that this is a panning type of motion. Okay, somebody is taking a camera and doing this type of panning. So it's not the dome is not moving, the camera is moving. That's why. Okay, so this is a very typical behavior of a panning sequence. Now, if you take a look at, so if you just simply take the frame difference, this is what you get. Take this, subtract that, display the absolute value, this is what you get. Take this, subtract that, taking into account the motion vectors. Motion estimations is really powerful in video coding because you generate, see, instead of encoding this image, right? If you do not do any motion estimation, you have to encode this image, you have to encode that image, right? Instead of encoding this image, you can just do encoding this image. So it's a lot easier. Okay, another example. Maybe this shows up a little better. Okay, you see all the red arrows? Those are the motion vectors. Okay, so at first glance, you see that these two frames look exactly the same, right? Mother holding her daughter, and doesn't seem like anything is different between these two. But if you take the difference between the two images, you come up with something like this. So it indicates that the woman is moving her head. The background stays. See, the pictures here stay, the picture here stays, so you don't have any motions in this background. The child seems to stay. She is staying pretty still, but the mother is moving. Okay? The mother is moving. That's illustrate local motion. Okay? Usually motion is very local. So if you take the frame difference, this is what you get. Okay? If you do motion estimations, this is what you get. And the fact that you don't have any motion vectors up here means what? Background stay perfectly still, you get 0, 0 motion vectors. Agree? You get 0, 0 motion vectors. So when I plot 0, 0, it doesn't show up here. Okay? It only show up, so for example, these guys might be 1, 0 or 1, 1. Okay, that type of thing. Now what happened to this arrow? And what happened to this arrow? What happened to these arrows? They're moving far away. Okay? Now this, I want you to observe another thing. Motion estimation, the way that we are doing it, is not perfect. Okay? It's not always match the exact motion of the object. It's not. It's an ad hoc procedure. We do not take into account the object. We only care about the best matching plot, no matter where it is. Okay? It can be really, really far away. I don't really care. Okay? As long as it gives me very, very small errors, and I'm happy, right? So in a lot of cases, especially when you have plots near the boundary, a lot of strange things happen. Okay? It just happens that this gives you the best match, and that's it. Okay? So, should we take a break? Let me check out what I have. Okay? This is in the past. This is in the future. Okay? How can we observe the future? We just delay. We just delay the operations. Okay? We delay the motion estimations. We capture the future frame first, and then we start the motion estimation process. Okay? So you can search over here in the past. You can also search in the future. And that turns out to be a technique we call bidirectional motion estimation. So B hat, which is this, the estimation of this block, can be a linear combination of C1 and C2. Okay? So it can be forward only. For example, A2 is 0. A2, alpha 2, right? Alpha 2 is 0, meaning you only search in the past. Okay? Or the best match happens to come in the past. And then it can be alpha 1 equal to 0, means the best match only comes from the future. Okay? Or it can be a combination of both for whatever reason. Okay? So in this case, you always get much better motion estimation. At what cost? Double the computation time and delay and very good. And agree? So that's where it will get you. Okay, and this is a demonstration of how sometimes using both backward and forward give you a better motion estimation. Okay? Now you can generalize this scheme even further. You can say, wait a minute, I'm going to do multiple reference frames. Right? So I use frame -1, use frame -2, and also use frame -3. Okay? To find the best match. I don't have to always have to use this same frame. Okay? So this is a technique called multiple reference frames, and it's actually being employed in H.264. This is where some of the largest improvement comes from. H.264, because you are. Now, do you have access to all these reference frames? Yes, yes, you encode them before. You just store them in a buffer. Okay, so that comes at a computational cost. Okay, first of all, you need to spend a lot more time searching because you can search here, you can search here, you can search there. And second, you have to buffer all these frames. Okay, so that comes at multiple costs, and thus make 264 a lot more complicated to implement than say MPEG-1. Okay, what about other variations? You can make your block size variable. Okay, at this point, we're searching in this mode only. 16 by 16 square, we don't consider anything else, right? Now, but when you have object moving, sometimes you do not capture the entire object using one block, or a block a block might contain both background and foreground, right? The foreground moves, but the background stays. Okay, so in that case, you might need to split the block up. Okay, and that's why sometimes you can improve by choosing this mode, searching this guy independently of this guy, searching this guy independently of this guy, or searching 4 guys independently, or searching 16 guys independently. So these are the modes. This is also the motion model for H.264. And you have to, how do you find out what mode is the best? How do you find out what mode is the best? Okay? What do you have to do for the decoder? You have to send the mode over to the decoder. Okay? And if you decide to choose mode 4, you better send 4 motion vectors to the decoder. Okay? So that increases side information to trade off for residue energy. The residue should decrease all the time, but the side information typically increase. Okay? I bypassed this. This is a little. This is actually in MPEG-4, and this is based on the affine model. So obviously you have a lot more parameters to find out. Okay? Some kind of global estimations, but the main point that I want to emphasize is that what we just discussed on both block motion estimations is the key to state-of-the-art video coding. Whoever does motion estimation, motion computation better will win. Okay, at least up to this point in time. Okay, and when we go back from the break, we're gonna start tracing back the history of video coding, starting from the earliest one to H.264 now, and you will see that everything from then to now, okay, is just minor variation of the same scheme that we have been talking about for the first roughly 2 hours. And from now on, we don't have, we will talk about video compression standards, so we're going to try to trace back the history of developments in this field, and hopefully we learn a few things along the way, okay? Maybe, first of all, differentiate the difference between different codecs, learn how the behaviors of different codecs, learn the way people engineer these things, okay? So this mostly is an engineering problem. It's not a mathematical problem anymore, okay? A lot of things that people do in video coding is very ad hoc, is very intuitive, works great, but as you can see, there's just not much mathematics that you can claim about anything, okay? A lot of times, all the choices that people make, all the thresholds that people come up with, okay, come from experimentation. Okay? People play around with a whole lot of test videos, okay, find out the modes, the thresholds, the whatever the behaviors that give you the best performance, and then set it as the default. Okay? That's typically how the way things work most of the time. Okay? And so the process of establishing an international standard involves a lot of these experimentation steps. Okay? People do a lot of experimental simulations, exhaustively study a lot of options that they have, and choose the one that seems to be consistently outperforming others. Okay? And that's why, as you can see, we have many different tracks of standards. Okay? There's some ITU, which stands for International Telecommunication Union. Okay? And these guys are mainly concerned with teleconferencing, real-time communications of video over the networks. Okay, so we have the H.26 series. Okay, H.26 series only deals with video, only deals with the video part. There's another guy that deals with the audio to go along with it. Okay, as we will see in the next few slides. And then we have the AMPAC standards, which is a different body, a different group, a different set of international researchers. And the main goal here is for archiving purposes. So you store for storage, for long-term storage and playback. You might throw away the real-time constraint. Okay, you can take forever to do motion estimation here if you want to. Nobody is gonna care because we encode the video once. Okay. And as far as, and if we can play back fast enough, then that's all we care about. Okay, so here, you might have more flexibility in terms of designing the codec. And so the first international standards for video coding is called H.61, as you can see here. And it started in roughly about 1994, 1995. And that's what, 20 years ago? 20 years ago. Imagine that. A long time ago, right? Okay? I wasn't even in the university yet, okay? So they started a long time ago, and see how long it takes to finish the project. It takes roughly all the way to 1990, 6 years to finish the project. Okay, you know what people do during that 6 years period? Okay, when people try to establish an international standard, there will be a call for proposal. Okay, the call for proposal will go out. Let's say the ITU would like to seek expert opinions on establishing a new video coding standard called H.61. Whoever interested, whoever has the best technology and would like to contribute, please come to this particular meetings and submit your proposal. So there will be a lot of proposals, okay? And then they have committees, okay, that judge a proposal. And the way they judge it is they run experiments after experiments after experiments after experiments. Like, keep on running experiments, okay? And nobody really submit the entire video codec. Okay? You only need to submit what is your expertise. Okay? Maybe your expertise maybe it's motion estimations. Then you submit that motion estimation algorithms. Okay? With certain input output so that people can just put it into the codec and make it run. Okay? But they have to test various modules, and they have to test various combination of the modules. And that's why it takes so long. Okay, and so that's what happens when people first establish HL261. So after HL261, there's some overlap with MPEG-1. Because these are two different committees, two different communities. Okay, there might be people participating in both. Okay. And then, so this guy gets started, and as the later one, it has the advantage of knowing what this guy has been doing. So you will see later on that a lot of features in MPEG-1 actually come from HL261 because people already know that this feature works well, that doesn't, okay, so on and so forth. So they borrow a lot of the popular features here. Okay, and then work out their own, their own set. So this gives you MPEG-1. Now, when people haven't finished MPEG-1 and they already started the project for MPEG-2. So MPEG-1 is designed for lower type of bit rate, and MPEG-2 is designed for high quality. High quality back then, not now, but as we can all see. DVDs looks a lot better than VCD. Is that correct? DVD image looks a lot nicer, right? So MPEG-2 is designed for high quality, and MPEG-1 is designed for lower quality type of archiving. Okay? So after 261, it takes people in ITU take a break, and then they started with 263, 263 plus, 263 plus plus, and plus means there's a little improvement from here to here. Still the same old standard, but more advanced features. Okay, and plus plus means it's the plus of this guy. So so after a while they say, okay, HL263 plus 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 is going to look ridiculous, so let's start HL264. Okay, so they name it an entirely different codec. Now, as you can see, there's no MPEG-3 over here, right? There's an interesting story on that. MPEG-3 actually got started, and they would like to design MPEG-3 for high-definition television, HDTV. So there are a lot of proposals, and then guess who is the winner? Something very close to MPEG-2. Okay, so they say, okay, in that case, we're going to scratch MPEG-3, and we're going to just use MPEG-2 instead. Okay, so right now, I don't think HDTV is very popular in Vietnam. Right? There's no broadcast. There's no HDTV broadcast here. But there has been a lot of HDTV broadcasts in the US. The quality is stunning. For example, the 64 matches of the last World Cup is all in HD, and I just had to buy my own HDTV for it. It's heaven enough. Okay, it's totally different.
Can you tell people the cost for HDTV display?
Well, there are many different kinds. The most costly is the 1920 by 1080. That's called 1080p display, and it can be like $10,000 easily. Okay, but the lower end, the mid end of HD is 1280 by 768 or 720. Okay, that one you can buy for about 3,000, and then there's another guys about. It all depends on the resolution of the TV. There's another guy also called HD, but doesn't quite have the resolution. It's 1024 by 720 or 768 or something. That one may be around 1,500. Okay, so they're still expensive, and the content. The main problem is the content. We don't have too much HD content to show. So even in the US, there are about 10 HD channels. and they are mainly National Geographic type of. So you get to watch a lot of nice vacation places and interesting animals and so on and so forth. But there's just not a lot of content right now. So I think it's going to take a few years for Vietnam to catch up. But we've been studying that problem for a long time now. That shows you the difference between cutting-edge research and real product coming out of the market. Okay, it takes a long time for these things to mature and becomes popular product as things that we can use every day. Okay, now so this gives you an idea of what has been going on in terms of setting up standard. Now, in the field of video coding, it's hard to have your own video encoder decoder unless you're Microsoft, okay? Because you, if people have various different kind of encoder decoders, sharing data, watching videos will be extremely difficult. You have to go get this codec, and it's really troublesome, right? So unless you're Microsoft and you integrate everything into the operating system, then okay, that's a different story. But for most of regular common people like us, we have to depend on these standards, because these standards tell you precisely how you should implement, you know, how you can design and implement a working video codec. Okay. Now, another thing about standard that I would like to say is that the standardized committee only specify the bitstream syntax. Okay. They only specify the bitstream syntax. You have to follow this rule and this rule and this rule and this rule so that the bitstream can be decoded by any decoder out there. Okay. What that means is they leave a lot of room for you to play around with. Okay. For example, it never tells you how to implement motion estimation. Okay. It only cares about, okay, feed me the motion vectors for this microplot. Okay. Whatever you do to get that motion vectors is up to you. So that's why there are various MPEG-2 encoder out there with various quality level. Because it depends on how the implementer decide to do a certain things. Okay? So that gives you a lot of flexibility to deal with, although it's an international standard. Okay? Now, so let's think about, take a look at 261, and I spend most time here because it's the first video coding standard, and then a lot of the other guys are just improvement over H.261. Okay? So this guy is designed for bit rates around 64 kilobits per second to up to 1.92 megabits per second, and it actually is an entire series. 261 deals only with video, but there is also the audio codec, okay, to go along with it, and then the synchronization, the system control, the multiplexing, all the hairy details that put the video and the audio together into a complete unified bit stream, and that's the system components. Okay, so the goal is to do real-time video phone and video teleconferencing at rather low bit rate and with a reasonable delay. Okay, so this entire thing, okay, is called this entire system is H.320. And it has the video codec, it has the audio codec, it has all the communication equipment, the system control, the end-to-end networking, everything muxed together into the final 320 bit stream. Okay?
Professor, what happened to delay there?
Oh, well, because sometimes you have to synchronize between the video and the audio. Certain part of the audio has to go with a certain frames, okay, so that you can synchronize, okay, especially when singers is singing on stage, right? Okay, you want the lips to match up with the audio. Sometimes there can be problem, but right. Now this codec is really simple. It fixed the resolution. Fixed resolution. It only works with SIP and QSIP. Okay, SIP is 176 by 144. QSIP is twice this size. Okay, and it breaks that SIP frame into group of blocks. Okay, so there are 3 group of blocks. 1, 2, 3. Okay, each group of block gets split into a bunch of macro blocks. Okay, and each of the macro blocks. So each of the macro blocks look like. So this is the size of the group of blocks. Okay, 176 across, 48 across. So you will see that there are 3 macro blocks in the vertical dimension and 11 in the horizontal dimensions. And each of this square looks like this, with 4 luminance blocks and 2 chrominance blocks. Okay, so this is the 16 by 16 square that we talk about all the time. Okay, this guy is what you're going to do motion estimation on. This guy is what you're going to do motion estimations on. After you do motion estimations, each of these 8 by 8 blocks will be grouped together, fed into the DCT through quantization, through entropy coding, and coming out the bit stream. Okay? So this is the hierarchical layer of H.261, and this is the block structure. Okay? So this is at the pixel level. So I'm going all the way from the frame level to the group of blocks level, to the macro block level, to the block level, to the pixel level. Those are the hierarchy. Okay? There are 2 modes, intra-coding mode and inter-coding mode. Intra-coding mode means the macro block is encoded as is without motion compensation. So in the case that you cannot find motion, in the case that there's a scene change, in the beginning of the video, you will do inter-coding, no motion. Okay? Inter means you will do block matching motion estimation. The motion residue will be DCT encoded, just like we played around with MATLAB yesterday. And the motion vectors is differentially encoded. Okay, what does differentially encoded mean? You take 2 neighboring motion vectors, you encode the difference instead of, okay, so we try to save some bit rate. Okay, so this is the intra-coding mode. In the intra-coding mode, the block comes straight to the bit stream. You don't need to do any motion estimation on the blocks, okay? But you still need to decode the block, because you need to keep the previously reconstructed frames in the buffer for motion estimation for the incoming frame. So you still need to do decoding right here. Okay? At the decoder, it cannot get simpler than this. At the decoder, you just take the bit stream, inverse entropy coding, inverse quantization, inverse IDCT, go straight to the display. Okay? No motion compensation. Okay? The intercoding mode is slightly more complicated. You, for each of the block, you have to do the input to the motion estimation modules is the reference frame. This is the current block. Xn is a block, the 16 by 16 square block. So that block gets motion compensated, okay? And then the difference between the motion compensated blocks and the original block is encoded and go to the bit stream. And this is the decoder. Okay? So this is the motion estimation in H.261 is exactly the same as the motion estimation that we talked about maybe half an hour ago. Okay? Exactly the same structures. Now, this is interesting. Okay, you guys already have some questions on search windows, the relationship between the search window and the performance of the video codec. And this slide is designed to demonstrate just that. Okay? This is a study from the International Standardization Committee when they established H.261. They test mainly video teleconferencing type of video, meaning there's mainly head and shoulders. People sitting around the room talking to each other. Okay? They don't do motion pictures or anything like that. So they do head and shoulder videos, and they investigate search window based on these diamonds. Okay, so take a look at option F. Option F means there is no motion compensation. What does that mean? Just take the frame difference, right? Just take the frame difference. There's no motion. You take the frame difference and you're done. So that is the 0-0 motion search. Okay, 0-0 motion search. You don't let your search go anywhere. Okay, you make it stay at exactly the same place. Now, option E is a diamond that is 2 up, 2 away, 2 up, down, 2 sideways. Okay, so 1, 2, 1, 2, 1, 2, 1, 2. Okay, that's the diamond E, and then diamond C, diamond A, diamond D, so on and so forth. So you have different layers, different search window size. Okay, and then A is the entire square, 15 by 15 that we talk about all the time. Okay, so let's see what happens. Okay, this is the search region A, B, C, D, E, F. Okay, hope that I'm missing F at the extreme side, but I don't know if you can see it right here, right here, right here, right here. Okay, F is always the worst performance, the worst performer of all. Obviously, right? You're not doing any motion estimation. You cannot expect to compete. Okay, so very bad, very bad, very bad, very bad. Okay, across all bit rates. Now, but then something interesting happens. Okay, take a look at option E, which is a very small diamond search windows. Okay, this option E gives you this performance. Okay, comparing. Okay, as you can see, this is almost as good as that one, this one, this one, and this one. So option E at very high bit rate works almost as well as the rest. Okay? Now, this only holds true for head and shoulder sequences, of course, because people, okay. And at high bit rate, what happens? At high bit rate, you can afford to send a lot of the residue. You can afford to send a lot of the residue. So if you can send a lot of the residue, you will get very, very close to the original signals, okay? So in that case, there's no difference. There's not much difference between all the options. Now, when you step down in bit rate, then E is not optimal anymore. Then you start having to, because you get squeezed a little tight now. Your communication channels only allow you to send a few number of bits. So then you need to do much better motion estimation to compete. Okay, and in that case, the BCD is still doing, ABC is still doing very well, but then D is already one level down and E is quite bad. Okay, so this is the higher you are, this is PSNR or signal to noise ratio. Okay, so you want to be high, you want to be high up. Now, if you go down to the lowest bit rates that H up to 61 allows you to do, which is 64 kilobits per second at 7.5 frame per second, then you need to do a lot fancier motion estimation. Okay. Another difference between these is the frame rate. This is 30 frames per second. This is 15 frames per second, this is 10 frames per second, and this is 7.5 frames per second. The more frames you have, the less difference between frames, right? Correct? Because you do finer sampling, and that's why you don't need a search window. You don't need a large search window if you have a high bit rate and you have high frame rate. So this is actually this experiment result also holds true for other type of sequences as well. Usually, if you have high frame rate and high bit rate, you don't need a large search window. You can just do a reasonable search window. And typically, your search window should always be around the 0-0 points, or the best approximated points that you come up with. Okay, and but by reducing the search window, motion estimation complexity can be significantly reduced, and that's one of the main strategies. Now, let me bypass this. This show you how to encode the motion vectors. So instead of sending the dx and the dy directly, okay, we should do dx and minus 1. So you only encode the difference, and that tends to give you lower bit rate. Okay. So I have one student asked me this question during the break. How do you determine intra and inter? How do you know? Okay. Well, you do experimentation, and then you come up with an ad hoc threshold, and the threshold happens to be behaving like this. Okay. 64 here, 64 here. This is the variance of the block, and this is the MSE, which is defined as the MAD square. Okay. So let's see if it makes sense. If you're over here, you have very high MSE. Should you do intra or inter? MSE already takes into account the reference, okay? So high MSE means you search, right? But the end result is pretty bad, okay? So in that case, you should do intra, correct? Okay? What about here? What about in this area? Why should you do inter? Oh, low MSE, right? Low MSE means you do very good motion estimation, correct? Then you should do inter. Now, the slope is not a straight line, but it's going like that because the variance tell you how complex the block is, right? The variance tell you if the block is smooth or the block has a lot of texture, okay? And typically, with a texture block, it's a little harder to do motion estimations, right? Because you have to match all the texture. Okay, so that's why experimentally it has been confirmed that if you use this line here, you tend to do slightly better. Okay, so the low energy, the high energy is the scene change. Occlusions means something that come into the frame and cover up some of the background. Uncover area means an object that moves away, that leaves the background exposed. Okay, those are scenario where you need to use intra mode. Okay, and the scenario where you need to use inter mode is when you have stationary background, you have low energy, you have translation and motion. Now, doing motion compensation or no motion compensation. No motion compensation means that you just copy the block over, right? Copy the block over, and again, this happens when the committee discover that this is a pretty reliable way to tell if you want to do copy or not. Okay, and you should verify by yourself why this is the case. But you can, as you can see, mainly because when the okay, so this is a trade-off between BD, which is defined as the 0,0 motion vectors, okay, and the motion vectors that are resulting from your search. Okay, so this is no motion compensation means you just copy the blocks over and you don't do anything else. You don't send anything. Okay, which is the simplest case. Okay. There's another features that 80261 has, which are the loop filter. So it's a very simple filters inside the block. So 121 divided by 4. Is that a low pass or a high pass filter? It's a low pass filter. It's a very good average low pass filter. Actually, it's one of the wavelet filters as well, right? The 3.5 wavelet, right? So this is you only apply this filters inside the blocks to smooth out the variations, and at the boundary you don't do anything. You do no filtering. So as you can see here, this frame without the loop filters has more locking artifacts than this frame. because I have the low pass filter that's smoothed out a little bit. Quantization. We studied this yesterday, and there are two types of quantization. For DC and for intra-DC, which is just like image coding, right? So as the average of the block is always has a high value. So in that case, you don't need a dead zone or anything like that, right? So you just do the simple mid-rise quantizer. But for inter-DC, inter means you already take into account the motion estimation compensation. For DC and AC, we have a double dead zone to generate more zeros, and that helps compression a little bit. Okay, this is the bitstream syntax, and there's just nothing to really worry about, okay, unless you really have to implement the codec. Okay, but what it means is this. Okay, and I'll just say a few things so that you understand exactly what bitstream syntax means. Bitstream syntax means you have to be very precise. At the beginning of the bitstream, you need 20 bits. Okay, that 20 bits is fixed. Okay, and that's how a player recognizes that this is H.261, but not MPEG-4 or whatever. Okay, so we assign 20 bits to describe that this is an H.261 bit stream, and it should be right in the beginning of everything. Okay, then after that comes the picture type. Okay, another 6 bits that describe is that the beginning frame, is it an I frame or intra-coded, or is it a P frame, which is use motion estimations. Okay, so we need all these things, and they are very precise. The one in red using fixed length code. The one in red use fixed length code, meaning that for every frame, for every layer, it's always use the exact same amount of bits for the red. But the one in green means that it can vary. Okay, it varies because it depends on how well you do motion estimation, how your video behaves. Okay, so the one in green has variation in the length. Okay, the one in red is fixed, etched in stone. Okay, now the main difference between, we talked about MPEG-1 relationship to 261 before. There's an overlap. Okay, so these are the main features that distinguish H.261 from MPEG-1. And as you can see, this contains a lot of improvement. So H.261 only allows you to do SIP and QSIP. Okay, because back then we don't have fast computers, we don't have fast communication channels, for example. And if you do anything more than SIP, we cannot decode anyway. So it has no value. Okay. Now MPEG-1 is different. MPEG-1 is for archiving. We don't have to worry about communication channel bit rate, so on and so forth. Okay. We will store it on our computer. So it can afford to have higher resolution. This is always 4:3 aspect ratio, but MPEG-1 you can feed it weird sizes if you want. Okay, it takes away that aspect ratio. This one has group of picture, and this one doesn't. This one has I frame, which is intra-coded, and P frame, which is predicted, the motion prediction type of. But it doesn't have the bi-directional. It doesn't have the bi-directional. Remember, we do motion estimation in the past as well as in the future. That only exists in MPEG-1. Okay, because it's archiving, right? You already have the entire video in front of you, so it doesn't really matter. You can always look ahead. But this is for communication, real-time communications. It's harder to buffer the future frames. So it bypassed the B frames. The target bit rate for MPEG is around 1 megabits per second. This is, as I said before, 64 to 1.9. Okay, you can only skip 1 frame or 2 frames or 3 frames over here. There's no restriction over there. This guy used integer motion estimation, motion compensation, and this guy used half pixel motion estimation, motion compensation. maybe I should go back and talk about this real quick. This is one of the major improvement between MPEG and 261. This has a larger motion estimation, larger motion range, and the end-to-end delay here is not critical at all. Who cares? Okay? As long as we can decode fast enough, then that's all there is to it. But delay here is very critical. It's for communications, right? You don't want the other side to wait a long time to see the pictures. Now, let me go back and another concept that allows you to have better motion estimation. Okay? So, my red, my pixels, my original video pixels is in red. Okay? Now, I will allow motion estimation, motion vectors to have non-integer value. Okay? That's the entire idea. I allow, okay, the way we have been doing it so far, our motion vectors will always give you an integer number, right? You either move 2 pixels away, 3 pixels away, 16, 14 pixels away, but you cannot move 1.5 pixels away, right? So this is if you do half pixel motion estimations, you allow your motion vectors to point midway between the pixels. Okay? Now, so that means you can have vectors like 1.5 and 3.5. Okay? And when you step down to 1 quarter pixel motion estimation, you allow your motion vectors to have values like 1.25, 3.75, so on and so forth. Okay? Now, the next step is how to fill in the blank, right? What do you mean by an object moving 1.5 pixel away? Right? Now, when object is moving very, very fast, okay, and you do integer sampling, you certainly will miss certain motion, right? So this is the entire idea of making the motions feel a little bit more continuous, okay? And you just use very standard bilinear interpolation to fill in the blank, okay? So these are the pixel value. You get this pixel here by taking the average of A and B, okay? You get this pixel here by taking the average of A, B, C, and D. You take the pixel here by taking the average of C and D. And you do motion estimation on this big one, on the bigger frame. You do motion estimation on the bigger frame. So that's all there is to it. Understand? Okay? So that's how you can have, if your block happens to sit right here, here, then you actually have half motion, pixel motion. Okay? Now, there's one thing that I can say. I can claim, I can make this claim, okay? The claim is, if I do sub-pixel motion estimations, my residue can only decrease. My prediction residue can only decrease. It can never increase. Okay? How do I say that? How can I make that claim?
It's not the decrease. It's the same classification the integer index before.
Yes. This is the superset, which include the integer points, right? Right? This space, this new space, which is twice the size, okay, include the original red pixels, right? Okay. So integer motion estimation is a subset of sub-pixel motion estimation. It's a subset. Okay, that means you also search the integer, points, but you also search the half pixel points. Okay, so in the worst case scenario, you always get the integer points back. Okay, so this is the reason why this can only decrease the residue. What increases is the side information, because it takes you twice. It takes twice. Your vector space has twice the amount of resolution. You have to describe the 0.5. Okay? You have to describe the 0.5, so you need more bits. to describe the motion vectors. Okay, so this is one of the main features that improve. So 263 is the follow-up of 261. Okay, and it is actually H.261 with many MPEG features optimized for low bit rate. So it's still low bit rate. It's geared toward low bit rate applications. It has a major improvement over 261. Okay, and it's roughly about 30% bit rate saving over MPEG 1. So this is a pretty powerful improvement over MPEG 1. So the 263 main block diagram is this, and this is the main features. Okay, this is the main difference between the two codecs. This is where the 3 dB's improvement comes from. Okay. Well, first of all, it's a lot more flexible. Okay. The group structure is different. Okay. The main things is here. The main things is actually here. As you can see, as you go from half pixel motion estimation compensation to full pixel motion estimation compensations, the improvement is roughly in the 2 to 4 dB range. Okay, you have a lot more flexibilities. Certainly the complexity goes up tremendously because we have to at least 4 times, right? Okay, because the size of the reference frame is 4 times the original size. But this is a tremendous improvement. Okay, there's no loop filters here, and there's also very smart coding techniques for motion vectors. So the side informations, in order to compensate for the resolution increase in motion vectors, we do better predicted motion of predicted coding of motion vectors, and that's how we keep the side information roughly the same. Okay. Now, H.263 plus, okay, is whatever we have here, and then add these features. Okay, these are the additional features that people put in. And right now, this is a very popular codec. Okay, if you buy teleconferencing equipments nowadays, okay, most likely inside you have H.263 plus in there. Okay, the source code is all over the web. It's very powerful. It's almost like MPEG 4. This is almost like MPEG 4. Okay, it has, these are the advanced features. It has unrestricted motion vectors mode, meaning the motion vectors can point outside of the frame. Okay, how do we do that? We symmetrically extend the frame on all 4 sides and allow the motion vectors to point to the extended. Okay, so sometimes there's an object that comes halfway into the frame. Okay, there's an object that comes halfway into the frame. You extend the frame, and you tend to capture the entire object, right? So the motion vectors kind of like point outside of the boundary. So that is one advanced features. The H.263 plus has the capability of breaking the microplot into 4 8x8 blocks, and then have each of the 8x8 block having motion vectors. Okay, that is an additional major improvement. It has something called overlap block motion compensation. It allows the neighboring blocks to contribute to the motion compensations. Okay? So we will not talk about these things too much because we don't have a lot of time. But these, if you want to read about, they are pretty easy to understand and implement it. It has adaptive arithmetic coding. The type of doing BCCD arithmetic coding that we talk about is the entropy coding engine. That is a significant improvement over Huffman. Okay, and then it has the PB frames mode. So in 263 plus, it actually has the capability of doing bi-directional motion estimation and compensation. So I'm gonna bypass these, okay, and maybe. The history comes like this. It's sitting right here. It got started roughly in 1998, 1997 or so. Okay, and it ends roughly in December of 2004. Okay, so this is the cutoff line for proposal acceptance. Okay, this is it. Now, it first started as HL26L, and then it becomes HL264, and then it becomes MPEG-4 Part 10. Okay, so it's had a long political history. Okay, the story is that the MPEG people evaluate the codec, they like it a lot, and instead of doing their own MPEG-4, MPEG-5 or whatever, they say, okay, you guys are so good, why don't you become, why don't we just adopt this codec and make it Part 10 of MPEG-4? Okay, so there's an MPEG-4 that they worked on earlier, which has wavelet technologies in it too, okay, which doesn't really perform too well. So they finally decide to adopt this thing. Okay, so this is so HL264 is known either as HL264 or MPEG-4 Part 10. All right?
John?
Yes.
You mentioned about this political fight, so maybe you can explain a little bit to the people what the motivation behind all of this, political push from the company's perspective.
Mainly from the industry viewpoints. A lot of the participants in these international standardization committee comes from the industry. Okay, and they have their own agenda in terms of who should win and who should not win, and what part of the proposal. There's fierce competition, right? Okay, everyone wants their technology in it, and want to block the competitors' technologies out of it. Okay, and there's voting and ballots and everything. Okay, there's a small competition between the MPEG people and the ITU people. There are a few participants that happen to participate in both. But other than that, there are people that just do MPEG alone, and there are people just do ITU HL26 alone. Okay, and they have a friendly competition back and forth. Okay. So for a short period of time, MPEG-4 outperformed HL263 Plus by a little bit. So they are the leading video codec. Okay. And then the ITU people come up with these things that outperform MPEG-4. So it's go back and forth. It's not mainly friendly in nature. Okay, but if there is competition, it's like what I said. You try to promote your company's technology, and you have a certain amount of bias. So the MPEG-4 people, sometimes in 2004, set up an official quality control check on HL264, and they noticed that their own MPEG-4 codecs is lagging behind quite a bit. So instead of, so basically they raised a white flag. Okay, they say, okay. If it's 2-3 dB like this, there's just nothing we can do. So this seems to be working out well, and this might have this seems to meet MPEG-4 requirements. So let's adopt this thing as part of the standard. Okay, so that you need to go to the meetings to notice these things. And as far as I know, we don't have any Vietnamese participation whatsoever. Okay, in this standardization committee. We might have a few overseas Vietnamese who works for other companies, happens to be jumping in and out of international standards. But now, there are some academic people in these international standards as well, okay? Because it's an open call for proposal, right? So if your lab has the latest video codec and you would like to participate, then go ahead and submit. Now, pay attention that you actually have to go to the meetings, every meetings. You have to lobby for your technology. You have to make friends with other people, so otherwise you will never win. Okay? Otherwise you never win, because people will find out a way to kick you out. Okay? So it's you have to really participate and set yourself up as a major contender in the field before you get acceptance and becomes a standard. Now, as I said, typically different modules, okay, different part of the algorithms get adopted, not the entire algorithm. Nobody in the history of standardization committees actually come up with a codec that will be holding true throughout the entire 6 or 7 years that it takes. Okay, so typically add these features in, take these features out, that kind of thing, and it involves a lot of experimentation. So it's pretty much the terms that I talk to my graduate student all the time, that a lot of things in video coding seems to be software tuning. Okay, you need to tweak parameters, and you just keep on tweaking parameters here, there. Keep on tweaking until you come up with a set of parameters that seems to be working pretty well. Okay, so that's what people do pretty much all day. Okay. Now, the coding framework, there's not much difference between framework-wise. H.264 is very similar to what we studied before. Okay, same old things, DCT, motion estimations, residue, encoding the residue. Okay, but there are a few keys. Okay, there are a few main features that really set it apart. Okay, it has some of these are new features for H.264. First of all, there's a compression improvement. Second, they have integer transform in there that allows you to do exact integer to the integer mapping.
Indicate interests he has, his location. There's automatically generated a list of...
Thing about this transform, anybody see? Symmetric basis functions, very good. Yeah, I'm pretty sure. This is orthogonal. Has integers coefficients. Integer coefficients. Right? Right? So you can perform the transformation using integer arithmetic. You don't need any. You can even implement this using without any multiplication, right? So you can do it pretty fast. And this is one of the innovations. Okay, we actually participate in this thing. So this is something taken from our BIN-DCTs, or the binary approximation of this. Now, so this transform is requires only 16-bit arithmetic, okay, and it has been expanded to 8x8 for other sizes. Now, the quantization has a lookup table. Okay, so basically they quantize everything using one single delta. Okay, the step size. But the delta, the relationship between the step size, the delta, okay, with the number you actually input into the codec is this table. Okay, so they want to increase, they want finer control of the bit rate by having quantization step size to be non-integers. Okay, the quantization step size here is non-integers, right? It has small increments. Okay? Oh, there's a typo. This should come before that. Okay, but yeah, it says they want small increments so that you can finally control the bit rate coming out. Okay? Innovation number 2, intra-prediction. This is huge. This is one of the main reason why it's doing so well. It has directional predictions of pixels when they do encoding. Okay, so you are allowed to choose mode. These are the modes. Okay, mode 1 is to predict your cell from the guy down here. Mode 1 is to predict yourself from the guy down here. Mode 2 means you predict yourself from the guy over here. Okay? And likewise, mode 3 is a diagonal prediction. Mode 0 is a diagonal up direction. Okay? So this is, and the way they do prediction is this. Okay? Now you can see, let's take an example. Mode 3. What is mode 3? Mode 3 is this direction, right? Okay? So you predict A by, you predict A, F, K, P. You predict these 4 pixels, okay? By this formula. A plus 2Q plus I plus 2 divide. Do you know what this means? Shift by 2 means divide by 4 and then truncate. Whatever, below the decimal points, okay? So what is A? A is this guy, 2Q. Q is this guy. I is this guy, okay? So you predict this edge, diagonal edge, by averaging A, I, and 2Q. Does that make sense? Right? That's a very nice diagonal edge prediction. Okay? And then if you pick mode 0, it will be different. Okay? If you pick mode 0, which is predicting that way, so then I guess M, J, G, D will be predicted by the L and the M down here. Okay? And that's the way they do it. Okay? And after the prediction, the difference between the predicted values and the prediction and the real values will be encoded. Okay? So they say bit rates that way. This is for intra-plot, right? Intra-plot coding without motion. Now, 4x4 intra-prediction mode, which is that, has these features, okay? And then the prediction in the larger plots, okay, is done this way. Again, it has 4 modes that allows you to do intra-prediction for larger plots, okay? Then, innovation number 3 is flexible plot motion compensation. This is probably the main reason why HR264 is doing so well. It has many different, basically 7 motion modes. 0, 1, 2, 3, 4, 5, 6. Okay? These are different block modes. And if you, it does exhaustive search for all these modes. For all the modes, they do entire, full search, motion estimation. Compute the SAD. Keep it. Move to block 2. Do motion estimations. Compute the SAD. Keep it. Mode 3. Okay, and then after the end, it checks to see who wins. Okay? The guy who wins got picked. Okay? The mode index is sent to the decoder, the motion vector is sent to the decoder, the residue is sent to the decoder. Okay? So it's a brute force algorithm checking everywhere and predict everything. Okay? That's why it's so slow, but its performance is so high. Okay? An example would be something like this, right? You have a tennis player, and the racket is obviously moving very fast. Okay? And so if this happens to be your micro block, and the object is moving fast, you will never be. So this is the background, right? Okay. This is the background, and this is the foreground. The foreground is the racket. The background is whatever it is behind. Okay? Maybe the scoreboard or whatever. Okay? So this is the background. This is the foreground. This block happens to contain both background and foreground. There's no way that this block is moving together. You actually have to split it into, these are the 2 background blocks, these are the 2 foreground blocks. And in this foreground block, maybe this is actually a background. This doesn't move. Well, it actually moves, but it doesn't seem to move. The racket is moving, but then all the strings look roughly the same, so it looks like a background. Okay, so this turns out not moving. This is not moving. This is not moving. But all these guys, these 3 might be moving. Okay, and that's how they do much better motion estimation, motion compensation, comparing to, say, MPEG 1, which is just doing motion estimation on this guy alone. Okay, and that's one of the main features. Innovation number 4, multiple reference frame. Another brute force, ad hoc, but very effective technique. You search over 5 reference frames, okay, exhaustively. Well, you can. You can. The standard doesn't force you to do so. You can just choose one, okay, and be standard compliant. However, if you want higher performance, you actually have to choose this mode, okay, being able to search within the last 5 reference frames and find out the best match, the lowest residue. How do they do that? Search frame 1, search frame 2, search frame 3, search frame 4, search frame 5. For each of the frame, search all modes. For each of the frame, you search all modes. And out of these 5 times 7 modes, 35 overall, you pick one winner. Okay? That one winner got sent to the decoder. So the way reference frame works is like this. As you can see, this block might come from this frame, this block might come from that one, this block might come from here, and it can do bi-direction as well. Okay, with multiple frames. So very powerful. Okay. Innovation number 5, deblocking filters. Okay. When you have micro block like this, and then you do motion estimation, motion compensation based on block wise. And one of the problems is that when you concatenate these blocks together in the decoder, there's a mismatch. There's a blocking artifact. We see blocking artifacts yesterday, didn't we? When we do motion, when we do we do that? Right, just for image coding, but it's similar, right? You do every block get encoded independently, right? And then you concatenate them together into the frame, and if you don't do anything at the boundary, there's no warranty. There can be a mismatch. There can be a mismatch, right? The mismatch comes up very annoying, blocking artifacts, okay? So you have to smear out the mismatch, okay? You have to filter out the mismatch. But you know that the mismatch only exists at the boundary. It doesn't exist inside, okay? So you should not filter everything. If you filter everything, if you take a low-pass filters and you just pass it through the low-pass filter, you're throwing away your real edges as well. You don't want to do that, right? So you want to adaptively just take a look at the boundary and just work on the boundary alone, okay? So that's another innovations that we have from 8.264, and this is one of the demonstrations. Blocking artifacts pretty much everywhere here, okay? And with the loop filters or the deblocking filters, you can see that all of these regions, which looks really bad before, turns out to be very nice and very smoothly. Okay. And this also helps in the encoding of the next frame, correct? The next frame coming in and get predicted from this one, not that. So then the motion vectors become, the motion prediction becomes much more efficient, okay? Because these edges actually can mess up your motion estimations. And finally, innovation number 6 is context adaptive binary arithmetic coding. So the arithmetic coder being used in 264 is binary. It only understands 0 and 1. Only understands 0 and 1. Okay? But it context adaptive, meaning it actually take a look at the neighbors, okay, and form a super symbol. Form a super symbol. Okay? And so we talked about that before, combining symbols together into a larger one. Okay? And innovation number 7 actually comes at the network layer. Facilitate the communications of these over a lossy communication channel. So how is the performance comparison? Okay? This is on the Foreman sequence, 30 frames per second. This is signal to noise ratio. The higher you are, the better. And this is the bit rate. Okay, MPEG 4 is in purple, 8.264 is in blue. And as you can see, if you draw the line of equal performance, meaning that the same reconstruction quality, the bit rate of this guy is what? It's around, this is in kilobits per second, so this is about, I don't know, 40 something, 42 something, right? And the bit rate, this guy is 190. Okay, so that's more than 4 to 1. Right, 4 times. In this case, for this particular setup only. And this is at a very low bit rate. Okay, so low bit rate means 264 will have a lot more power because it do all these exhaustive search. Okay, when you start moving to high bit rate, the performance difference is not as drastic anymore. Okay, but still, this is a major improvement, right? And the quality for the, if you take a look at the 2 frames, 39 kilobits per second here look almost as good as 203 over there. What about other standards? Okay, so these are, this is 264, this is MPEG 4, this is 263, this is MPEG 2. Okay, and as you can see, MPEG 4 is roughly 263. MPEG 4 is roughly 263. Okay, they have so many things in common. Okay, so that's why they are so close together. Okay, and then MPEG 2 is what you see on your DVDs. Okay, now let's draw an equal line of performance. Okay, if you draw the line right at 34, okay, this gives you 50 kilobits per second roughly, and this gives you roughly about 100. So twice the bit rate. Okay, in this particular case. What it means is that for the same DVD, you can have 2 movies now instead of 1. Same disc. Okay. With, and I blow it up, so that's why it looks bad. But should I blow it up? Okay. Anyway, I want to show you this. We draw lines. We draw lines to show you the way that H.264 actually partition the blocks. Okay? And in the beginning, every block gets labeled as I. I means intra. Okay? That means there's no motion estimations. Okay? You just encode the block. I4 means the block is actually got split into 4 smaller blocks for encoding. I16 means they get encoded as a large one. So as you can see, all these things are so white, it doesn't contain any information, so they got encoded together. But this guy is complicated, so it got split into 4 by 4, okay? And then you have more similar things inside. Now, let's step through this thing one, okay? So here, all the motion vectors will be in blue, and the partitioning of the blocks become like this. And as if you notice, Classical has the bus moving. The bus moving against the background, okay? So you should expect motion down here only, but not here, okay? The building is not moving. There's a small little flags here that's moved, but okay. Most of the backgrounds stay the same. So as I step through, you will see that all the motion vectors follow the bus. Look at the motion vectors. Yes. The one in blue. It follows the bus. See that? It follows the bus. Now, and the partition is also a lot more busy down here. Okay? Because in order to capture the bus, you actually have to partition the blocks a whole lot more than things up here. Okay? And then when you start going here, oh, it's become crazy, right? Because you have the dome moving, things are flying all over the place, okay? So motion vectors are all over the place. This frame is very costly to encode. It costs a lot of bits. Okay? Yeah, and it turns out that we're not, even with the splitting scheme, we're not doing motion estimation very well. Okay, there's a whole lot of errors here. But at least all the motion vectors seems to be pointing uniformly in a direction, which indicates that there's a lot of consistency. in the motion here. Okay, so the dome look like that. There's the CP stand for copy. So for whatever reason, those blocks matches very well with one of the guys in the previous frame. So it get copied over only. So some of the block here, for example, I4 indicates that they do motion estimation here, cannot find anything interesting. So okay, intra-coded this guy. Okay, that's the entire idea. And as you can see, the codec is so adaptive. It's searching all over the place for the best mode, okay, and choose it, then send to the decoder. Okay, let's see anything else is interesting here. Maybe let me show you some. This look like the Empire State Building in New York City. Okay, so let's see. This is okay. Let me just play it. Okay. So this is a helicopter flying around at night, capturing New York City's skyline. Okay. It seems pretty dark up here, but on my computer it's actually nice. You can see a lot of details. You can see cars, you can see people. Okay, this is so there are a lot of looks like camera motions here. What happens? Okay. Yeah, this is like looks like fair of some kind with rotating wheels for little kids to. So now let me show you something interesting. Okay, the video 1280 times 720. That's the mid-end HD high definition resolution. It tells you how many frames you have, the aspect ratio, the file size, you know, a whole lot of other information. Okay. Now I can do, if I do this, it will show me all the motion vectors. Okay. So let's go back and watch the sequence again with all the motion vectors being shown in red. So these are the motion vectors, and as you can see, the helicopter is moving this way. So most of the time you see horizontal motion vectors. Okay. And oh yeah, there are actually a lot of smaller ones. Small ones. Okay, here it should go crazy, right? There's a lot of motions. There's a lot of motion. Some of these things are in red, so you don't see the motion, but there's actually a lot of motion. Okay, there's movement in and out so fast. Here, all the motion vectors are pointing together, so they seem to be connected, but they're actually a sequence of motion vectors here. Okay, this block point over here, this block point over there, so on and so forth. Mode, when you see red, is intra. That means no motion estimation whatsoever. And in the beginning, every guy is intra. Okay? In the beginning, every guy is intra. Then we have yellow and blue. I believe yellow is copy. That means you just call the blocks over. And blue is the one that actually has some motion compensations. Okay? So you see a heavy yellow flavor. There's a lot of copies, okay, and a lot of blues, very few reds, unless there are scene changes. Okay, so let's notice notice that. Okay, I will see a lot of yellows. Those are the copies. Okay, and then I see a lot of blues, but you can see a lot of red as well. Those are the blocks that HL264 has problem doing motion estimation. Okay, so this is okay, and let's see what happens in the scene change. There was a scene change that roughly you see all reds, right? Okay, so and now here there's a lot of reds. There are a lot of reds because we just failed to find motion vectors, appropriate motion vectors for it. So this sequence, at least for this part, it contains a lot of motion. It contains a lot of motion. So you see all these guys, they have problem finding the appropriate motion vectors.